so far we have taken some 2 port and then found the formula for its incremental y parameters. Now we are going the now we are trying to figure out what the characteristics of the device must be, of that box must be, the IV characteristics must be, so that the incremental parameters look like this. Does it make sense, right? So, in other words, remember that if you had a general nonlinear 2 port, the current in port 1 was some function f of V1 comma V2. What we are saying now is that, and what was Y11? Dou f by dou V1, and we want that to be equal to, what do we want that to be? 0. And similarly Y12, which is dou f over dou V2 must also be equal to 0, correct. So, what is one function that satisfies this? Well, I1 is a constant, and what is the simplest constant that you can choose? Actually, it can be any constant, but special case is when I1 equals 0. Okay, it's just a special case, it could be any constant. All right. So, what comment can you make about the input characteristics? I mean, it's either a constant and the constant can be 0. I mean, so there is no fun in drawing a constant straight line. So, I mean, there is no point in drawing the input characteristics, right. I mean, it is a constant. I hope that after people as old as us should be able to imagine a constant without having to show a picture, correct. Okay. Now, the second what is Y21? Is dou g, remember, is some other nonlinear function of V1 comma V2, all right, and so Y21 is nothing but dou g by dou V1. We want this to be large, and Y22 which is dou g over dou V2 must be 0, all right. So, what comment can we make about the function of? Very good. So, now we should draw the output characteristics. Okay. And the output characteristics, remind me again, what are we trying to draw? I2 on the y axis and V2 on the x axis. It is telling us that the incremental Y22 is 0. So, for a given value of V1, what comment can we make about the output characteristic? What are the output characteristics? I2 versus V2 for a certain, I mean, it is a family of curves, each curve is for a specific value of V1, and we vary V2 and measure I2. So, for a specific value of V1, if the incremental Y22 is 0, what does it mean? The output current does not change if you change the output voltage. Okay. So, basically V2 is independent, I mean I2 is independent of V2. Okay. This is for some specific value of V1, let us call that Va. For another value Vb of V1, what do we expect to see? Another straight line which is parallel to this line. Okay. Let me call that and for yet another V 1 which is equal to V c, you see yet another parallel, correct. Okay. Now, if the difference between V a and V b was very small, where again we will come back later and qualify what the meaning of small is, then what comment can you make about the spacing between these lines? So, in other words, if V b minus V a was a small signal, correct, what does the distance between these two parallel lines, what does that quantify? Y21 times delta V. Is that clear? So, as you keep changing the voltage, absolute voltage at port 1, the lines, you get a family of curves in the output characteristic. And ideally, for a small change in V 1, you would like the spacing between the characteristics to be very large, and that indicates a large Y 2. Is that clear? All right. Now, I do not know if you remember, but what did we say about this box? I mean, where are the energy sources? Are they inside the box or are they outside the box? They are outside the box. So, this box is passive, correct. So, it can't be generating any energy. So, what must be satisfied? What are the constraints if that box is passive? What comment can you make about the port voltages and port currents? V 1 I 1 plus V 2 I 2 must be greater than or equal to 0. In the special case that I 1 is 0, what comment can we make? So, V 2 I 2 must be equal to, must be greater than or equal to 0. In other words, the output characteristics must lie in the first and third quadrant. Okay. So, now we are looking at the first quadrant, all right. So, now can these lines extend? We said they have to be parallel to the x axis, correct. Can they extend like this into the second quadrant? Why? If they extended into the second quadrant, then the device would become active, which means there is a source of energy inside, which basically we said is not the case. And therefore, if these characteristics so, if since this device this box is passive, it follows that these lines cannot remain parallel to the x axis for all values of V 2, right. They can only be in the second quadrant or either in the characteristics can only be in the first quadrant or the third quadrant, right, and they cannot be parallel to the x axis for all values of V 2. So, how do you think so if so this characteristic therefore will have to dive into the third quadrant, and what do you think a reasonable way of doing that is? Well, one way of that happening is basically doing something like this, right, and the same thing holds for all these characteristics, correct. And it is not necessary that I mean this knee point is the same for all curves, it is just something that I have drawn here, right. But for a given V1, eventually the characteristic has to dive into the third quadrant, right. Okay. So, if you want to have any amplifying 2 port, the characteristics that you see must look like this, okay. And all that we have used is, I mean this does not depend on whether there are electrons, whether there are holes, whether there is, I do not know, I mean there is a molten ion inside the device, okay. This is if we want to have a device or a 2 port that amplifies, these will be the characteristics. And this just is plain conservation of energy and basic arguments that are enough to establish that these must be the characteristics. Does it make sense? Right. Now that we know these characteristics, we go to our device colleagues and say, can you make a device like this, and they say sure enough, okay, and not merely one kind, we can make all kinds of devices, all of them, but all of them will eventually end up having characteristics like this, right. How many of you have seen characteristics like this before? Transistor, right. And how many transistors are you, kinds of transistors are you familiar with? You are familiar with the bipolar junction transistor, you are also familiar with the MOS transistor, right. And I do not know how many of you are familiar with the JFET, heard of something? Yeah. And its characteristics also look similar, right. There is also transistors you can make with gallium arsenide, right, it is called the gas FET, right. That also has got characteristics which look like this. And forget about silicon or semiconductors, like long back, even before your grandfathers were born, there was an active device called the vacuum tube, right. The characteristics of vacuum tube also look like this, except that those those variables are called something else there. One is called plate voltage something, right. But the output characteristics of that vacuum tube also look like this, and the vacuum tube has got nothing to do with diffusion, drift, all that stuff. It is pretty much you have a plate, you heat the plate and then you boil electrons off the plate, then they go from place A to place B, okay. So, the physical phenomena involved in carrier transport are extremely divorced from what you can see in semiconductors, right. And even in semiconductor devices, all of you probably know from your device classes that the bipolar transistor, for instance, it operates, is it a diffusion device or a drift device? It is a diffusion device. A MOSFET on the other hand is a drift device, right. So, the physics of operation of the two devices are completely different, right. Bipolar is something you inject some carriers into the base and then some recombination, all sorts of fancy stuff, whereas MOSFET is you apply a voltage, attract some electrons to the interface and then apply voltage across the drain and source, right. But if you look at this, you can see that all that stuff, they are all details which are irrelevant as far as the basic box is concerned. Tomorrow, I mean 10 years or 15 years from now, if some new device is invented with quantum tunneling, this thing, that thing, all that, you do not have to worry, because the characteristics will have to be something like this, right. The only thing that will change is the formula, that what is the only thing that is left to be described here. I mean what the exact function that does this is the only thing that remains to be described, and that is going to be a function of how you make the device, whether you make it with semiconductors or whether you make it with cement or whether you make it plastic, it does not matter. That is only going to alter the nature of that equation, but the fundamental nature of these characteristics are going to be the same, right, okay. Which is why to be a good circuit designer, you really do not need to, it is not as if you need to go deep into you know, how electrons are jumping, how for, you know, Fermi levels, energy density, you know, all that stuff. That's all good stuff that you know, is fun stuff to learn, but that's got nothing to do with your competence as a circuit design, right. It is like a civil engineer, right. I mean, you know, I mean, it is true that the building is made of bricks, correct, and it is made, it's got iron in it, right, to hold the structure. But I mean, you know, as a civil engineer, do I really care whether the iron was treated at, you know, was brought from Bihar, or whether it's bought from Germany, or whether it's heated in blast furnace or whatever? I don't know. I don't care, right? As long as the iron doesn't, you know, bend over and break, okay, I'm good to go. All right. Same thing with the brick. I don't need to know the details of it was boiled at this, I mean, it was cured at this temperature, it was, you know, it was mined at this place, all that stuff, they are all irrelevant details. All that I need to know is, will, you know, how heavy the brick is, will it be able to withstand this load and all that stuff, right. So, as long as the input output characteristics of the box or the brick is known, the details of you know, the chemical phenomena or the physical phenomena occurring inside are completely irrelevant to me. Likewise, if we know the characteristics of the transistor, I mean, of this box, which, you know, is the transistor, from an input output terminal point of view, in other words, if we know the expression for this current, this I2, basically the only thing that we need to know is this function g, right. Once you know that function g, the rest of it is, you know, is not relevant, right. Whether it's diffusion, drift, you know, tunneling, this thing, quantum, you know, whatever, right. None of that stuff is relevant as a circuit design. If you are trying to build devices, of course, that is the bread and butter, but if you are trying to build circuits, you do not need to worry about it, okay. All right. So, having said that, so we go to the device folks and basically say, well, can you give us a device like this? And they say, yeah, sure. Here is one possible device, and I mean, so it, so you know, there are many possible devices, and then, you know, depending on economics and all that, you know, we pick one device and use that in our, as an example to illustrate circuit design, right. The examples with minor modification would be applicable to any device, all right.